Welcome to Calculus. Being challenged has a whole new meaning. On this episode, Stevenson will demonstrate
Now you've seen how we can use slope fields to graph a general solution. From a general solution graph, you can actually then sketch the particular solutions, and I showed you that one in my previous videos how we had the sine wave, right? If we knew an initial condition, we can kind of sketch the particular solution in our slope field. It's pretty cool. But Euler's method is actually a way where you can directly graph or sketch the particular solution without even needing a slope field. In other words, you don't need the general solution. You can actually use the idea of local linearity and connect all these little line segments together to create a continuous approximation of the curve. Now, you may have heard of Euler's method from movies such as Hidden Figures. Please understand, in movies such as those, they take really complicated math ideas and oversimplify them. Was Euler's method actually used? I don't know. Maybe do a little research and find out. But it has been brought to light, made famous because of Hollywood.
The problem is when the capsule moves from an elliptical orbit to a parabolic orbit. There's no mathematical formula for that. As we can calculate launch and landing, but without this conversion, the capsule stays in orbit. We can't bring it back home.
Maybe we've been thinking about this all wrong.
How's that?
Maybe it's not new math at all.
It could be old math. Something that looks at the problem numerically and not theoretically. Math is always dependable.
For you, it is.
Euler's method.
Euler's method.
Yes,
That's ancient.
but it works. It works numerically.
That's it.
Let's type it up.
So here's what Euler's method actually is. You have to start at a specific location. You have to know what your slope is, that's your differential equation, and you have to know how you're going to increase, what's your increments. So that's your delta x. But remember, if you change horizontally, you're also going to change a certain amount vertically. And you can see there's some formulas in there and so forth, and it shows you how to do this process. And you repeat this process over and over again until you end up at the desired location that you're trying to approximate. So I'm going to show you. Now let me show you how we can take that method and apply it. Now you are going to need your calculator, so make sure you have that handy. So let f be the function that satisfies the initial value problem, where the derivative is x plus y. So that's the differential equation. And the initial condition is f of 2, 0. Okay, so that means the point is 2, 0, which is right here. Use Euler's method and increments of delta x at 0.2 to approximate f of 3. So our goal is to figure out what is f evaluated at 3. So in other words, we know the input. The question is, what's the output? Okay, so our goal is to get from 2 to 3 using Euler's method, using little delta x's or little increments of 0.2. So let's set up our table. So this is your ordered pair. Here's your derivative. Here's your delta x. Now delta y is whatever the derivative is times your delta x. Okay, so that means this number times this number will go here. And then your new location is where you started plus how much x changed, and then the y coordinate is where you started plus how much y changed. Okay, so let's go through this. Here we go. So what's dy dx here? Well, dy dx tells you just add the two coordinates together. So 2 plus 0 is 2. Delta x is 0.2. Now what's dy dx? Well, dy dx is 2 times 0.2, which is 0.4. Now I know some of you probably could do that in your head. I just want to show you that you're going to do lots of calculations here, so you make sure you have your calculator handy. Now, my new point. So where did it start? 2. How much did it change in the x? 0.2. So that's just 2.2, comma. Now where's the new y point? Started at 0 and it changed by 0.4, so 0 plus 0.4 is just 0.4. So now this is where it started, this is where this line segment ends at. So this is where my new line segment begins on the next column. So I'm going to run through the process a second time. Again, my goal is to end up where I have 3 over here, and then whatever the y-coordinate is, that'll be my answer to approximate f of 3. So let's go through it again. Now, what's dy dx? It's this plus this. So 2.2 plus 0.4. Delta x is the same. Now, delta y is delta x times dy. Okay, so now where's my new point? Well, it started here on the x, plus 0.2 is 2.4. Where's my y-coordinate? Well, my y-coordinate was at 0.4, and now this is how much more it changed. Okay, so in my second iteration of Euler's method, I ended here. So for my next line segment, that's where I begin. So now I'm going to run through this process again and again until I end up with an x-coordinate right here at 3, and then I will stop. So I went through my Euler's method and I stopped here because I ended at my input of 3. So what's my output? So using Euler's method, f evaluated at 3 is approximately 3.46496, or you could round and say 3.465. Okay, so here is my approximation. And it took me 1, 2, 3, 4, 5 iterations at 0.2 increments. Now, let's talk about Euler's method and whether it's over or under approximations. Well, it depends on the behavior of your curve. So if your function is concave up, what happens with Euler's method is you have a starting point, and then you end up building all these little line segments, that's what we're doing, to match it. So you can see it's going to be an underestimate. But if your function's concave down, you have a starting point, you can see as you build your little line segments, it's going to be an overestimate or an over-approximation. So how your function is behaving will help determine whether this is an over or under approximation if you apply Euler's method.